This will be a video covering NMR spectroscopy, known as nuclear magnetic resonance spectroscopy. We're going to be covering the theory behind it, how the actual machine works, how signals are extrapolated, how they're split, how you can differentiate structure in different proton environments, and then we'll give quite a few examples and show you how you would determine what the NMR structures would look like on the readouts. So just a quick overview of what NMR actually is. It's generally the most commonly used technique for determining the structure of an organic compound. It's very useful identifying hydrocarbon skeletons where functional groups are attached. One of the key points about it is you only need a very, very small amount of your compound in question to be placed in the NMR tube to be read. It's non-destructive for the most part for your molecule. Depending on what solvents your molecule can be dissolved in, it might be a little bit more destructive. But generally the amounts are so small, it's not that big of a deal for most synthesis labs. From just a simple reading, you can determine an incredibly large amount of a large number of the information about the molecule in question. Be them protons, the positions of the molecule of the protons. You can measure different nuclei. It doesn't have to be proton NMR, which is the most common, which is mainly what we'll be talking about. You can take readings on, carbon isotopes, fluorine, phosphorus, a whole bunch of different molecules you could read depending on the complexity of your specific NMR instrument. Proton NMR, also you'll see the 1H NMR representation. Basically, this determines the chemical environment the protons are in the molecule. That's why it's so commonly used for organic compounds, hydrocarbon skeletons, because you have an abundance of protons of these hydrogens in most of your molecules. And then probably the second most common would be the C13 NMR reading the placement and environments of the carbon nuclei. And for all of these, you'll notice the isotopal readings for each of these elements. It's because basically you could use these isotopes as specific markers, and it's a lot easier for your NMRs to lock on to the isotopes versions to have a good baseline for your material. Like if you were doing a proton NMR, usually use some type of deuterated solvent, either heavy water, deuterated chloroform, deuterated dimethyl sulfoxide, stuff like that, that can solvate your chemical in question and have a proton source that can be tracked and locked on very easily by the NMR. So the physical basis of NMR revolves around something called nuclear spin. All subatomic particles have a spin, and the protons and electrons are charged. So when we're talking about the protons in the nucleus, and generally the entire nucleus, because nucleus is just, of course, protons and neutrons, will have a total overall spin of overall positive spin. So anytime you have a positive spin or any type of charge on a molecule and it's spinning, that creates a magnetic field. So when these spinning charges happen, this magnetic field is generated, and depending on the arbitrarily assigned by chemists and physicists, the direction of the spin, either to the right or left, up or down, however you want to orient it, when you do quantum calculations, you get a spin value of positive or negative 1/2. I'm sure you remember this from your general chemistry when you're doing the filling up those little electron configuration boxes, quantum numbers. Your m sub s, or spin azimuthal number, can only have a positive or negative 1/2 value. That's what those come from, and that's the actual value quantum mechanically when you solve for the orbital equations and wave functions doing Schrodinger equation. That's what you come out with the angular momentum values of positive and negative 1/2. In a normal molecule, your nuclei are oriented in just an infinite variation of ways in space. So here's a good representation of what it actually looks like when you don't have a magnetic field or any presence. Now, when this magnetic field changes, everything that's spinning aligns parallel to an applied field. So everything lines up. And for NMR, we're going to use that as kind of a set point. Now, in addition to this aligned set point, we also have to take into consideration that you can have two different spins for these nuclei, and the energy required to have a nuclei spinning one direction is directly proportional to the energy required for it to spin the other way. It just have a different charge or a different phase. So you have a set point in the middle, and to have it spin, say, arbitrarily to the left, it has to have a certain delta E. And to spin to the right, it has the same delta E, just in the negative value, or vice versa. It's all arbitrary based on how you perceive it. So up can be the negative way, down can be the negative way. It just doesn't matter as long as you keep it consistent throughout all the calculations and everything. But the key is you have that steady state in the middle where there's the arbitrary no spin. And to make the nucleus spin one way, you apply a certain amount of energy in a specific direction, or negative or positive charge. To spin it the other way, it's the same amount of energy, it's just the opposite sign. So it's a negative value instead of positive, or vice versa. So the important thing here is the frequency of this EM radiation, the kind of like with IR that we talked about in the previous video. It's completely different for different elements. And it's also completely different for different isotopes of the same element. So you're also able to tell isotope versus, C12 versus C13, H1 versus H2, stuff like that. So NMR is very concerned with basically the nuclear spin orientation, or the change in direction of that spin is specifically what it's reading. Because we use a strong radio generator, radio wave generator, to set everything in one specific way, and then we hit it with an orthogonal pulse, and it spins everything the other way. And then we can measure the time it takes to return back to the steady state, what spins in contrast to what doesn't spin, how long some things take to spin, stuff like that. And you're able to tell a whole bunch of information in those spin orientations. And that's actually what NMR is, nuclear magnetic resonance. It's that resonance in the spin states where it can go back and forth due to the absorption of radio frequency radiations. So that's the key point is of NMR. It's all about the change in spin direction of your nuclei of your atoms in question. So the frequency of the absorbed EM, the radio waves, is totally dependent on the environment that the specific nuclei you're looking at it can be found in. So just a single solitary proton has a completely different energy required, or energy absorptions, than a proton bound to a carbon, or a proton bound to an oxygen, or two protons bound to a carbon, or a proton bound to a carbon that's bound to another carbon with three protons. The chemical environment is everything. That's why you can elucidate so much information, because of all the things that spit out. When you read it in NMR, you can see chemical environments, you can see what's bound to what, you can see what's next to what, all from pulling out this data and doing mathematical extrapolation on it. So it's a pretty big tool. And because everything has a different chemical environment, and chemical environments can change so quickly and even small little distances intermolecularly, we have to take all that into account. And nuclear shielding plays a big part, because not all of the nuclei see the same charges, not all see the same pull from electrons or repulsions from other nuclei. Things get shielded based on how much is around them in comparison to other nuclei and other atoms. So there's a whole bunch that goes into this. So if we have theoretically, if all protons were exposed to just a set magnetic field, they would all absorb the exact same frequency of energy, because it's just protons. It doesn't matter what atom it is, it's protons. It's just a single subatomic molecule. But in actuality, the electrons are circulating in clouds around and have different densities in different parts of a molecule. So basically that shields those nuclei quite a bit. Repulsive effects or attraction effects, different angular momentum, stuff like that. So basically, they're spinning too, and they're causing their own tiny weak magnetic fields of their own. So the molecule is just a magnetic field upon magnetic fields, and then you apply a total magnetic field to that. So there's just tons and tons of interactions, just a mind-boggling number of interactions. So what happens is all those different little tiny areas of weak magnetic fields that the electron clouds generate, those shield the nucleus a little bit from the initial big man-made magnetic field we're applying to it. So based on how many electrons are around it, different chemical environments, all the nuclei in a molecule don't feel that same initial magnetic field. So the greater the amount that is shielded, the lower frequency is going to be required to produce a resonance. So we can use that kind of in terms of like a polarity. The more polar a molecule is, it's going to have greater shielding. The less polar it is, it's going to have less shielding, stuff like that. So you can kind of extrapolate based on the frequency of your peaks to see is it a structured elucidation for a polar molecule, is it non-polar, is it aromatic, stuff like that. So that basically ties into where on the chart you're going to be seeing specific structures. Now with NMR, you hear a lot when you start reading into it and taking readings and listening to people talk about it, is something called chemical shifts. Now chemical shifts is basically just a measure of how shielded, like we were talking about in the previous slide, how shielded a nucleus is, a specific nucleus of a specific atom in a molecule. So depending on the amount of shielding, the chemical is the peak that you see for those protons in association are going to have a different chemical shift. Now they're shielded either greater or lesser. It can be upfield or downfield, and it's all based, like I said, on the environment. And when we're talking about environment, we're talking about, is this bound to a carbon that has other protons on it? Is it bound to a carbon just by itself? Do the attached carbons have protons on it? Is there an oxygen near it? Are there protons 2 carbons away, 3 carbons away? Is the molecule symmetrical and has multiple, like for instance, methyls are attached around a central carbon, but they're all the same? All of that goes into account in terms of different chemical shifts. So we need some type of reference system to base everything off. And what chemists and physicists have used is something called tetramethylsilane, and it's abbreviated TMS. Now, this is incredibly a very, very highly symmetrical system, tetramethylsilane. So it's a silicon-based molecule with 4 methyl groups attached on it. And the protons are very highly shielded, and they're shielded because of the symmetry and the way silicon works and some other reasons. They're incredibly highly shielded, and they generate basically just a single pure chemical environment. Everything looks the same to an NMR. So we use that kind of as a zero out to have everything as a nice baseline. And this is if everything was exactly the same chemical environment, this is what that peak would be. And then everything is based off of that. So everything is going to have some type of increased differences in chemical environment compared to the tetramethylsilane. Now, some more terms we kind of have to look at when you start reading an NMR, which we'll do a little bit later in this. But the terms upfield and downfield, I think I even used them before just out of habit. So basically, downfield means there's decreased shielding, and it's going to be further to the left on your chart. Upfield means you have increased shielding, and it's further to the right. You notice on the chart at the bottom, those values on the bottom are actually going to be measured in ppm or parts per million. We'll go over that in a little bit. But the big dark dash line at the 0 mark, that's your TMS, that's your standard, your tetramethylsilane. Right there, there's the chemical CH3,4SI, that's your tetramethylsilane. And the chemical shift is also denoted as a D, or parts per million. All of this is measured, really, remember this is always relative to your tetramethylsilane. Okay, talking a little bit about how substituents or functional groups of a molecule are going to affect the shielding. Electronegative substituents decrease the shielding. And remember, if you're decreasing the shielding, it's going to be further to the left on the NMR readout. So, for instance, right here we have a fluorine substituted methyl group, and the delta is 4.3 ppm when it's measured in NMR. That's how they're read. You'll get a specific peak at 4.3 parts per million on the readout. You've got an oxygen group. You got an ether there. That's at 3.2. It's very polar, but not as polar as the fluorine, so it's a little less. Then you've got a nitrogen group inside your molecule there. It's part of an amine, and that's 2.2. Still polar, but not as polar as oxygen and fluorine. Then you have just a pure hydrocarbon there, and that's a zero point 0.9 ppm. That's generally going to be your difference between the standard and the tetramethylsilane there, and your pure hydrocarbon is it's less than a part per million in terms of the change in chemical environment. Even though those are nonpolar, it's a nonpolar molecule. There is some ever so slight differences in a hydrogen environment versus a carbon environment. A little tiny bit of like induced polarity here and there. More electrons generally will go around a carbon than a hydrogen, so that you get some stuff here and there. But those are some key differences there, where electronegativity, as it increases for your substituted atoms in your molecule, the shielding is going to be decreased for all your methyl groups. And here's just the chart on the bottom. That's basically what it's going to show, how things are read out on an NMR. Your tetramethylsilane there at 0, and then there's your hydrocarbon, just pure hydrocarbon, a little bit further downfield, and then your nitrogen substitution, a little bit more electronegative. Further on is your oxygen, and then finally your fluorine. Now, when we're talking about electronegativity and shielding changes based on the methyls that see things, the effect is cumulative, meaning if you have multiple substitutions, they just keep adding to the standard effect. So, for instance, here we've got a tri-substituted chlorine methyl group, a di-substituted, or a single substituted. And if you notice, the single substitute is 3.1, so it's downfield because of the polarity difference, electronegativity difference. But as you add that second carbon, it increases more, and the third carbon increases even more. So looking at it on a standard readout, there you have this is where the single substitution would show up for chlorine. There's your double substitution, and then you try further downfield. Another thing to be aware of from NMR is anytime you have protons attached to an sp2 hybridized carbon, that's less shielded than an sp3, and consequently the same thing, an sp is less shielded than sp2. So when we have something like just a pure hydrocarbon, that's sp3, it's at a 0.9 ppm. Here we have sp2 carbons with the double bond, the alkene, that's at a 5.3 ppm. And here we have a aromatic system, basically, we conjugated alternating double bonds, and that's at a 7.3 ppm. So you notice all of these, same thing as the effects are cumulative. So the single double bond there, 5.3, you got 3 of them at 7.3. The multiple sp2 hybridized protons are going to keep adding to each other. So they're less and less shielded as you get more and more of them. Okay, with some of the basic, simple information, of course, I don't expect you to understand really any of this yet. We need to start going over some examples and stuff later on. But with some of that basic information and some basic extrapolation of what we can do and some of the physics behind it, you can kind of glean some pretty important information from just a simple proton NMR. The number of signals you'll see will tell you how many different types of hydrogens you have in the molecule. And types of hydrogens is basically the chemical environment those hydrogens are in. Okay, so the number of signals, say you have 6 signals, that tells you you have 6 distinct different chemical environments that the protons are involved in. All right. Number 2, the position of the signals, or the chemical shift, how either far upfield or downfield, determines what types of hydrogen. If they're hydrogens that have polar groups that are electron withdrawing, or if they're just pure methyl. If they're pure methyl, they'll be further upfield. They'll have closer to the TMS. If they have a lot of electronegativity associated around them, they'll be further downfield. So they'll be closer to 5, 7, 10, stuff like that. Now, stuff we haven't talked about yet, but each one of these peaks, the area under these peaks, you can integrate that and determine the area under a peak just from doing the calculus on each of these, the functions for these peaks. That tells you how many hydrogens of each type you have. So say you have 3 methyl groups attached to something. Each one of those methyl groups has 3 hydrogens. So if you have 3 groups, that's 9 hydrogens that have that same methyl environment. So when you would do the integration of that specific peak for those methyl, which wouldn't be too high because it's pure methyl, it'd be around 0.9 ppm, you would get a relative value compared to everything else of 9. So it would be 9 times more area under that than, say, something that just had one proton in its own unique environment. And then there's something called a splitting pattern, which we'll talk about here pretty soon. That tells you how many neighboring hydrogens there are. So it tells you the chemical environment of the hydrogens next to, or what's bound to, the area around it. So with an NMR, you're able to get, the number of different types of hydrogen in the molecule, what types they are in terms of chemical shift in environment, how many of each environment can be found, and what their neighbors are like. So with those 4 pieces of information, you can basically get the entire structure of a molecule if you know what's in it. It's pretty powerful tool. Okay, we'll do some really simple number of signals practice here. Okay, so when we're talking about number of signals, we're talking about how many different environments or how many different types of hydrogens you have in the molecule. So we'll start with the easy one first, the cyclohexane, top left there. So we have a 6-member carbon ring, that's a sp3 hybridized. So each one of these carbons is going to have 2 hydrogens attached to it to make everything nice and happy. So the first thing you should notice here is this molecule is perfectly symmetrical. No matter how you slice it, in what direction, horizontal, vertical, diagonally, dihedrally, it doesn't matter. One side of the molecule is exactly the same as the other. So that's going to be kind of a clue. So each one of these carbons has 2 protons attached to it. And each of these carbons also has 2 other adjacent carbons that also have 2 protons. So everything is exactly the same. And because everything is exactly the same, it's all the same chemical environment. So each one of these protons basically sees the exact same thing as all the other protons. So in this case, with the cyclohexane, even though you have 6 different carbons with 2 protons each, so a total of 12 different hydrogens attached to this molecule, every single one of those hydrogens has the exact same chemical environment. So there's only one chemical environment. Therefore, there's only one type of hydrogen, and you would only see one peak for this molecule for a proton NMR. Okay, going to the top right now, we have a methyl substituted alkene. So we got the carbon-carbon double bond, and if you notice the double bond carbon, there's no protons associated with it. And remember, this is proton NMR, so all we care about is protons. So we don't even care at all about that double bond. Doesn't matter in the slightest in terms of looking at the protons for number of signals. We just care about the different types. So the only place you see protons is in those methyl groups. But again, just like the cyclohexane, if you notice, this is a perfectly symmetrical molecule. Each of those carbon-carbon double bond carbons has 2 methyl groups attached to it. Each one of those methyl groups is just singly bound to a carbon. So every single proton that you see there sees the exact same chemical environment. Therefore, they're the same type of hydrogen. Therefore, you only see one peak, one signal, same as the cyclohexane. So, of course, to figure out the difference between, if you had these 2 molecules and you want to see which one it was through NMR, you'd have to use more information. You'd have to use integration area of the peaks. Remember, cyclohexane had 12 protons versus the second molecule only having actually it has 12 as well, so you'd have the same integration, so you couldn't tell that. The signal splitting would tell you a difference though, because it tells you what's adjacent, and then we get some different things because everything's the same adjacent in the cyclohexane, whereas we have difference in adjacencies for the alkene. So that's where you would be able to tell the difference between those 2 structures on the NMR. All right, now the bottom left, that's a benzene ring. So that's sp2 hybridized carbons. It's got a pi conjugated system of electrons in a ring in the center of the molecule. And there's only one hydrogen on each of those protons. But, just like the cyclohexane, it's a perfectly symmetrical molecule. Same chemical environment. All the protons see the exact same thing. So there's only going to be one signal. There will be a difference here because there's more electrons, there's more shielding, it's going to be higher downfield than the cyclohexane. So you can tell the difference between a benzene and a cyclohexane on an NMR. But just in terms of the number of signals, there'll just be one signal. All right, and our final molecule on the bottom, the paramethyltoluene, I'm sure there's a simple name for it. But this molecule, if you look at it, is also symmetric. You cut it in half, it's the exact same both sides. But there's a slight difference. Um, you notice the two methyl groups, they're exactly the same. Each one of those methyl groups sees the exact same thing. You can transpose a molecule, it's the same either way. So both of those, all those protons, those 6 protons on those methyl groups are in the exact same chemical environment. So you're going to see one peak for those. But we also have 4 other hydrogens in this molecule. Those are the hydrogens that are in each of the carbons on the side of that benzene ring. So each one of those is in a different chemical environment. But those are still all the same chemical environment because each of those 4 that are attached to the benzene ring are the same. Each one of those protons that's attached to that benzene ring sees an adjacent carbon that's attached to a methyl and an adjacent carbon that's attached to another proton. And no matter how you spin the molecule, look at them, that's the same thing. Each one of those has the same adjacencies. They're all for the same chemical environment that's on that thing. So all 4 of those are just one type of hydrogen. So you've got the methyl protons there that are in their own chemical environment, and then you've got the benzene protons that are in the separate. So in this molecule, you would actually see 2 signals. So this molecule shows the 2 chemicals on the top have 1 signal each. The benzene on the bottom left is 1 signal, but the methyl substituted on the bottom right has 2 different environments. Okay, still doing number of signals, but these are a little bit more in depth. This can show you how you can start getting different number of signals. So we got the top left molecule. First thing you do is find the protons. We've got 9 protons here, and they're all in methyl groups. But if you notice, each one of those methyl groups is actually exactly the same. They're all on an sp3 carbon, and they're all bound to another sp3 carbon. So they're all the same. So even though that's a little bit more convoluted, and you have an electron withdrawing group, that bromine there, that makes you think, oh, maybe something's going on. It's not. It's the exact same environment. They all see the same thing. So you would just see 1 signal for that. Now on the top right, you have bromoethane, and now we start getting a little bit something different. On the terminal, it's the CH3. Those protons are different environmentally than the CH2 protons, because the CH3 protons are on an sp3 carbon that's attached to a carbon. So that's what it sees. It sees that other carbon. But the one in the middle, the CH2 group, those protons see both the methyl protons to its left and a bromine to its right. So it's not a symmetrical molecule. It's a little different. And because of that difference, you have 2 different environments for your protons. So you've got the methyl proton environment, and then you've got the CH2 that's attached to the bromine environment for the protons. So you would see 2 different peaks, 2 different signals for that molecule. Bottom left, just adding 1 more carbon in there, you would expect, because it's a non-symmetrical molecule, that's a 3rd different environment. And that's what when you take this molecule's NMR, you see 3 peaks. You see the methyl peak, you see the first CH2, which is different from the second CH2. The first CH2, going from left to right, of course, is attached to a methyl and then to another CH2. The second CH2 is attached to a CH2 and a bromine, so it's a different chemical environment. Different shielding, different electronegativity, different polarity, stuff like that. So you see 3 peaks there. Then on the final molecule, the bottom right, you've got your 2 methyl groups, which are the same. They're both attached to that central CH. So those 2 are going to have the same environment, so that's just 1 peak for those 2. But then that central CH, that's a different chemical environment. They're attached to the methyls and the chlorine. It's different than the other 2. So you would see 2 specific peaks for that one as well. All right, we'll go over one more set of number of signals, because number of signals is probably the most important part, because once you get to that, then you go to splitting and shifting and stuff like that. But the number of peaks is the most important. So your top left molecule, if you notice right off the bat, hopefully at this point you've seen enough of these and started thinking about it, that you see 4 different chemical environments. You might be a little bit confused because of the methyls on the end, both end, but just notice what they're kind of around. The methyl on the left is around a carbon that has a bromine attached to it. The methyl on the right is around just a pure hydrocarbon. So that's a slightly different environment, so they're slightly different. So each of the 2 methyls are their own environment, so there's 2 there. Your carbon hydrogen that's attached to bromine is completely different from everything else. And the CH2, those protons are completely different from everything else as well. So you have 4 different environments there. So 4 signal peaks is what you would see. Now, the top right, we've got a central CH2 and then 2 terminal CH2s that have a chlorine substitution. So if you look at it, the protons on those chlorine substituted carbons are exactly the same. The molecule, if you split the molecule right down the middle of that central carbon, it's the exact same molecule on both sides. So those 2 on the end, those 4 protons that are attached to the carbons that have the chlorine substitution, are the exact same chemical environment. So it's just 1 peak for each of those 4 protons. And then the central carbon is just bound to other carbons, and those protons are in their own chemical environment. So that will only have 2 peaks, one for the CH2 in the middle environment, and then another peak for both of the CH2Cls on the ends. And then finally, our disubstituted chloromethyltoluene at the bottom. We've got the benzene ring, and then we've got 2 substitutions, one methyl group and a chlorine substituted methyl group. So this looks like, oh, we got a whole bunch of environments, but it's actually not as much as you would think. There's actually only 3 in there. Of course, you've got the protons on the methyl. It's completely different from everything else, and it's a non-symmetrical molecule, so that's its own environment. You've got the 2 protons on the CH2Cl. That's its own chemical environment, so there's 2. And then those 4 protons that are left on the benzene, they're all the same thing. They're just protons that are sitting on a sp2 hybridized benzene ring that just see the same thing. They're all the same. So you have the 4 hydrogens on the benzene, that's 1 signal. The 3 hydrogens on the methyl group, that's 1 signal. And then the 2 hydrogens on the CH2Cl group, that's another signal. So 3 signals for that specific molecule. Okay, we did a little bit exhaustive there of the number of signals. Now we'll move on to chemical shift. And this is going to change where things are on your NMR readout, how far upfield or downfield things are, based on the amount of shielding the protons see. So generally, if you just have protons that are on a primary hydrocarbon, a primary carbon, you're going to have a 0.9 ppm. As you get to a more intricate structure, secondary, tertiary, stuff like that, you start going more and more downfield. So a secondary, a proton on a secondary carbon would be a 1.3, even though it's just like a CH2 compared to a CH3, which is 0.9. Tertiary proton would be a 1.5. When we talk about something like an aromatic system, benzene rings, you're talking about, anywhere from 6 to 8.5. It's going to be a lot further downfield. Allyl groups are going to be 1.7. That's pretty consistent around there. Benzyl groups, or basically benzyl rings that are as a functional group, that's a 2.2 or a 3, where it's not the key point of the molecule. Now, when we talk about things like your chlorides, your bromides, that affects the hydrogens that are directly attached to the carbon that it's attached to. And that changes the shift of those protons quite a bit, because that's an electron-electron group. It's got a ton of electrons around it, so it's a whole bunch of shielding. So it's going to be further and further downfield. So your protons associated with the chloride go from 3 to 4 ppm. Bromides from 2.5 to 4. Iodides from 2 to 4. Alcohols, same thing. There's an oxygen, so it's withdrawing electrons. So your alcohols are protons associated with the carbon in the alcohol, not the hydrogen on the oxygen, but the hydrogens on carbons that are associated with the alcohol. So 3.5 to 4. Now, the hydrogen that's associated with the oxygen in alcohol is a little bit different. It can bounce anywhere from a 1 to almost a 6. It can show up anywhere. The key with that is variable, because just like with IR, it's hydrogen bonding. So it's going to different molecules. It's moving around constantly. And because of that, in NMR, generally you see just incredibly sharp, thin, precise peaks. When you see an OH, that hydrogen from an OH on an NMR, it's smudged out. It's a broad peak. It's generally the only time you're going to see a broad peak. So anytime you see an NMR with a broad peak, you've got an OH group there. That's a key thing to think about, kind of with like an NMR, and the same thing, broadening out. So that's just some basic ideas of what things can get shifted chemically by your chemical environment, the protons see. And here we have the dreaded shift range chart. Um, this is kind of a handy dandy tool. You'll see these in a lot of textbooks. You can see a lot of online, some better examples, stuff like that. But this is how you know, until you master NMR and use it all the time, which is pretty rare unless you're an organic or a inorganic synthetic chemist type of thing. Um, these things, there's really no way you can memorize this. There's just so much. And as you notice, a lot of these things, the range you can find them is huge. Like down the bottom, just look at, ROHs, the proton for the alcohol. Like we said, it can be anywhere a little bit less than 1 all the way to over 5, almost 6. Your amide protons have a big range. Your aromatic phenols have a huge range that's different than the standard uh, alkane based, non-aromatic based alcohols. Aromatics have a big range. So it's, everything has a range. So, but this is just a good guideline where if you see a peak, say you get a peak somewhere in the, say 8 range, if you look down at that, there's a good chance it has an aromatic. It's aromatic. It could be a phenol. It could have an amide associated with it. So you can kind of narrow things down just based on where they are on your chemical shift range charts. And of course, the good part about computers and everything is, they do all this stuff for us. They can remember all this stuff, whereas, it's a lot harder for us. So they just spit it back out to you. Okay, and if you've never seen one before, this is what an actual NMR readout would look like. Of course, it says toluene and there's the chemical structure for toluene. That wouldn't be shown, but the peaks and the ppm chart on the bottom, that's what you would see when you spit it out. So if you're looking at the toluene molecule, hopefully by now you can see there's 2 distinct chemical environments. You've got the methyl group protons, and then all of the protons associated with the benzene ring are their own group. So you got 2 specific groups, A for the methyl and B for the protons on the benzene ring. So as we said, the CH3s are generally around a 0.9, but remember this is attached to a benzene ring, so it's a little bit different. And there's shielding, so it's going to be a little bit more downfield. So we see that chemical environment for those methyl protons to be about a little less than 2.5, and that's because of the electrons that are interacting and shielding those protons that are associated with the benzene ring next to it. So it shifts it a little bit downfield. Now the B is the protons that are associated with the benzene ring. And as we said earlier, aromatics, protons associated with an aromatic ring, are generally between 7, 8, somewhere in that range. And we see for this molecule, they're a little bit above 7. Now we won't go into the integration. We don't show the integration here, but to do it, you would find the function of those peaks, and you would just integrate that function and get the area onto that curve. And then also there's something called splitting, which we haven't talked about yet. But splitting, it determines adjacent. And if you notice, there's like little side peaks and extra peaks that are kind of attached to these. And that's splitting. That's basically when this resonance happens, a bunch of different modes happen, and you get different interactions based on what's around, the number of protons around. And you can see how many splits there are, and that tells you how many protons are adjacent to it. So we'll talk about that a little bit later, but I just wanted to show you a basic NMR readout to see what they look like in case you hadn't seen them before. Okay, we're going to use the same 4 molecules, actually the same 10 or 12 that we did for the number of peaks to now look at the chemical shift of these peaks. So in your cyclohexane, the very first one, A, we only have 1 chemical environment, so there's only going to be 1 peak. And each one of these is a sp3, so you can expect the peak to kind of be near the 0.9, that the standard sp3 carbon. The only difference is these aren't terminal carbons or your primary carbons. These are all secondary carbons. And remember, secondary is a little bit further downfield. So it's actually probably going to be greater than 1 is what you would expect for something like that. So on the top right, we've got the same thing. We've got 1 chemical environment, as we already discussed, so just 1 peak. And normally they're all terminal carbons right there, but they are bound to another carbon which has electron density in that double bond. So again, they're not going to be the 0.9. They're going to be a little bit further downfield because of some extra shielding and some electron density around there. But they're not just a methane type thing. So it's not the pure 0.9. For the benzene down at the bottom, like we said, anytime you see just a pure benzene ring or any aromatic system, those protons are generally going to be in the 7 to 8 range. So 7, 7.5, somewhere around there is what you would expect for those protons, single signal. And for this is actually called paraxylene is the quick trade name for it. You got one peak for your two methyls and another peak for your protons in the benzene ring. The benzene ring protons you would expect a little bit greater than 7, and that's basically going to be the same because the methyl groups don't change their shift very much. But the methyl groups, because they're attached to the benzene ring, that's going to change their shift more than a standard 0.9. So those are going to be further downfield. So those would be a little bit more than 1 as well. Okay, now in the little bit more convoluted system, your top left, the tertiary carbon with the bromine and the methyls. It's all the same environment for the methyls. That's fine. But we do have a bromine in the situation. So that's putting a lot of shielding in the system. So it's going to be a lot further downfield. So we might expect these, even though there's sp3, CH3 carbons, they should be around 1 or so. We might expect this to be closer to 2 because that bromine is pretty highly shielded. Now on the bromoethane, on the top right, we've got 2 different environments, so we got 2 signals. And the key here is you got that terminal methyl group, so that's 1, maybe a little bit above because it's not just a pure methane, but a little bit above. But the protons from the CH2 are going to be a lot further because it's directly attached to that bromine. So they're going to be a lot more shielded. They're going to be much further downfield, even more so than the protons in the first molecule there. Your bottom left, the bromopropane, the one bromopropane, sorry, your methyl group, terminal methyl group at the end is going to be the closest to your 1. Your B environment, the CH2 in the middle, is going to be further downfield because it's not a primary carbon, and there's a bromine kind of close to it. And then that final CH2 that has the bromine attached is even further downfield. So you have 3 different things. The C is further downfield than B is further downfield than A. So it's basically you're just seeing which area has the most shielding, which area has the most electron withdrawing from it or electronegativity in the area, and that's going to be the furthest downfield, the one that's shielded the most. And then finally, your final molecule there, your 2 methyl groups are the exact same. They're attached to another methyl, so they won't be at the 0.9. They'll be a little bit past 1. But then your proton in the middle that's attached to the carbon, since there's a chlorine attached to it, that's fairly strongly electronegative. So that's going to be a whole lot further upfield than those others. So there should be a big range between those 2. And by the way, all of these molecules that we're discussing at the end, I show you their actual NMR, so you can actually see what's going on and see where each one of these are. And we'll get there sooner or later for this video. And then our final 3 molecules we talked about, top left, we have 4 chemical environments. And the 2 terminal methyls are going to be slightly different because one is closer to that bromine. So that's going to be further upfield. So A is going to be the furthest, further down. So A is going to be the furthest upfield, the closest to 0. B is going to be your next closest to 0. It's going to be greater than 1, but it's going to be closer. And then between your D and your C, the D is the carbon that's attached to the bromine. So that's going to be your furthest downfield, pretty far downfield. And then your C is going to be between B and D. So going from right to left, from 0 to more positive, closest to 0 would be A, then B, then C, then D. For the molecule on the top right, we've got 2 distinct chemical environments. The CH2 in the center is actually going to be A. That A environment is going to be the closest. It's there's 2 carbons attached to it. So it's not going to be the 0.9. It's going to be probably closer to 1.5 or so. But then the B environment chemicals have chlorines directly attached, so that's going to be much further downfield. So there'll be a big separation between those 2 peaks. And then finally, your last thing, your last molecule there, 3 chemical environments. Of course, the benzene environment of the protons is going to be 7 to 8, somewhere in that range. Your methyl group attached to a benzene is going to be greater than 1. And then your CH2 group attached to chlorine is going to be a lot higher than 1. It's not going to be as high as the benzene, but it's going to be, 4 or 5, probably somewhere in that range, I would expect. Now, in terms of integration, this is basically impossible to see with the eye. You would have to use computer software to do this. That's what they're good for. And this is how we determine all this stuff. But just some basic examples, some stuff here. Your bromopropane, you got 3 different chemical environments. And if you notice, for your A, that environment, that peak for the CH3 group, there's 3 hydrogens in there. B has 2 hydrogens and C has 2 hydrogens. So when you do take these peaks and do their integrations, you'll notice the ratios of these 3. The area underneath, A will be 3 to B to C is 3 to 2 to 2. So your B and your C will have relatively similar values, plus or minus a small amount, but they'll basically be, when you normalize everything, a value of 2, and your A will be slightly bigger at a value of 3. So you can tell based on the ratio of the area under each curve how many protons there are. So the second molecule there, you see you have 2 distinct regions of methyl groups for A, and then that CH for B. So A has 6 protons total. So when you do the integration, since B only has 1 proton, A will be 6 times larger in the area under the curve than B when you integrate. So it'll be a 6 to 1 ratio. So looking at our 10 or so molecules in question, cyclohexane again, 1 environment, 12 total protons, so you would see a relative area of 12 when you integrate that 1 peak. Your second molecule there, you have again 12 total protons in 1 environment, so again it would be a 12 value when you integrate the peak. Your benzene is going to have a value of 6 because it's non-substituted, so 1 hydrogen for each carbon, 1 proton for each carbon, so that'll be an integration value of 6. And then your paraxylene will have 2 chemical environments. The methyl proton environment will have a peak of range of 6 value for the integration, and then your benzene ring environment will have a integration value of 4, so it will be a 6 to 4 ratio for those 2. Moving on with our next group, we have 3 methyl groups, all the same environment. So that's 9 protons, so you'll have a integration value of 9 for the peak. Your bromoethane has 2 different environments, one with 3 and one with 2, so it'll be a 3 to 2 ratio for the integration there for your 2 different peaks. Your bromopropane has 3 different environments. One has 3 protons and your other 2 have 2 protons, so it'll be a 3 to 2 to 2. And of course, you can tell the difference between the two peaks, the B and C, by their chemical shift. C is further shifted downfield because of the bromine than the B would be. So that's how you would differentiate between those 2 peaks. And the final molecule on the bottom right, we have 2 chemical environments, 2 methyl groups, so that's 6 hydrogens, compared to the 1 proton on the central carbon, so that would be a 6 to 1 ratio of the area under the curves. Moving on to the final 3, we have our 4 chemical environment molecule on the top left with the bromine substitution, second carbon. The 2 methyl groups, they're different environments, so different peaks, but they both have 3 protons, so they would have a general relative area under the curve of 3. Your CH with the bromine just has 1 proton, so that would just be 1, that would be your smallest. And then the CH2 would have 2 protons, so that's just a integration on the curve of 2, so it would be a 3 to 3 to 2 to 1. Top right, you just have 2 environments. The central CH2, 2 protons, so that's just 2. And then your 2 CH2Cls just have 2 protons as well, but there's 4 total protons, so that would be an area of 2. So A would have 2 to 4B. And then our final molecule with 3 chemical environments, benzene ring. Your methyl has 3 protons, so that would be a 3 integration value. Your CH2Cl, just 2 protons, so that would be a 2. And your benzene ring has 4 protons associated with it, so that would be a 4. So it would be 3 to 2 to 4. So as you could probably tell how quickly we went through that and how hopefully easy that is for you. The integration is the easy part. And that tells you how many protons are in each specific chemical environment. And now we come to splitting, the most annoying part of NMR for most students. So splitting happens when protons are not structurally equivalent. That means you have, say, 6 equivalent protons, whereas they might be chemically environment might be very similar, but due to adjacencies and stuff like that, their structure isn't quite the same. And a good example here is what we show is 1,2-chlorodiethane versus 1,1-dichloroethane. And the big difference here is, and the 1,2-dichloroethane, you see those protons are basically exactly the same. They're structurally equivalent. So you're just going to see one peak for those protons. Now, if you look at the 1,1-dichloroethane, those aren't structurally equivalent. You have 3 protons on one carbon and just 1 on the other. So what happens there is because they're not structurally equivalent, we're going to have 2 different peaks, like 2 different environments. But because also the adjacencies of stuff is different, and the overall structure isn't symmetric, it's slightly different than, for instance, the 1,2-dichloroethane, which is perfectly symmetrical down the middle. You're going to get splitting. Basically, what happens is the magnetic fields of adjacent protons is going to overlap and cause resonance in the other protons. It makes it even more convoluted. So if you notice on the 1,1-dichloroethane on the right, the red hydrogens on the methyl group there, those 3 hydrogens, you're actually going to see 2 lines in that peak. And that's basically a splitting. That's going to be called a doublet because there's 2 lines. And that's split because there's an extra adjacent hydrogen. And we'll talk about a little of Pascal's rule, but basically the splitting rule is n+1. However many adjacent protons there are, you add 1 to it, and that's how many splits there are. So those 3 protons on that methyl group see 1 adjacent proton that's going to interfere with their magnetic environment, and it's going to cause it to split. There's 1 extra proton, so it's a splitting of 2, so it's a doublet. Now, if you look at the kind of yellowish-orange proton that's on the carbon with the chlorines, that's just a single proton, so it's a much lower integration value of 1 compared to the 3 for the other one. But the thing here is it's got 3 protons adjacent. So you would do the n+1 rule, so that would become a 4. So what you actually see, instead of just 1 peak for that hydrogen, you see a quartet. You see 4 specific peaks. Now, the common splitting patterns for these, singlets is just a single line. That's when everything's symmetric and you've got the same chemical environment. You get a doublet when you have 1 adjacent proton. You get a triplet when you have 2. You get a quartet when you have 3 adjacent. Quintuplet when you have 4. It's stuff like that. If you really get higher than 5, you start calling it either convoluted or a multiplet, because it's really hard to see unless you have really high resolution NMRs and really good printout of these specific NMR readings, and you can zoom in on it and do some calculations to see. But the splitting comes from adjacent protons and their magnetic field interacting with the protons in question. So like I said earlier, splitting pattern always follows n+1 rule. So the n is the number of protons that are neighboring, and generally what you do is it can be up to 3 bonds away, but for most things 2 is fine. If you want to go really in depth, then you'll be able to extrapolate some more stuff. But 1 to 2 away is really the key. 3 away, it starts getting really convoluted. So just a couple examples there. And the top one, we just have that 1 proton, nothing adjacent proton wise, so it's just going to be a singlet. The second example, you got a proton that's 1 carbon away, so that would be seen, so it's a doublet. The second one, you got 2 carbons, so you got 2 protons that are adjacent, so 2 + 1, so you get a triplet. And then finally, you get 3 protons adjacent is a quartet. Now, in addition to the number of peaks when things split, you also get the size differentiation between the peaks. And the size differentiation, the number of splitting is always n+1. The size differentiation is Pascal's pattern. I don't know if any of you have seen this before. That's factoring, and a lot of mathematics works off Pascal's pattern. Pascal's triangle, you might have seen it as too. But as things go up, the size of the peaks change as well. So if it's a singlet, of course, you just got 1 peak. It's a 1, size of 1, arbitrary size of 1. If it's a doublet, you've got 1 adjacent proton, and so you'll get 2 peaks because it's the n+1 number of peaks. but each of those peaks will be roughly the same size. You'll have the same area under each peak. So that's the way to look at it. Now, if you have two adjacent, then you start getting some weird stuff. You get an n+1 value of 3, so you get a triplet, and you'll have on that triplet, your two outer peaks will be the same size roughly, but your inner peak will be about double of those outer ones. And then when you go to a quartet, it's 1 3 3 1, and then when you get to a quintet, it's 1 4 1 4 6 4 1, and that's the general area under each one of those peaks. That quintet, triplet, quartet, whatever you're talking about. So that's how things extrapolate out, and that's just because of resonance upon resonance and multiple overlapping magnetic fields. That's just the way things work out. Now, there's a couple key things to note about splitting that can convolute things. So you've got these neighboring hydrogens, but if you have even different environments of neighboring hydrogens, say you have hydrogen a group 1 carbon away and it's got a different chemical environment than a neighboring group has, then you start getting convoluted patterns. You see complex patterns. And this is when you start seeing those multiplets where you get more than 5. That's because the interactions are so complex that it's really hard to differentiate between things. So if you see a signal with like 12 or 13 peaks, then there's a bunch of weird environments. Neighboring hydrogens aren't all the same or symmetrical. So that's where those complex multiplets arise from. Now, the other caveat is the proton on oxygen, alkyl hydrogen. That generally doesn't split. So generally you're going to get, it's in that 1 to 5 range, you never know. But the key to that, again, is the broadness. It's not going to be that well-defined sharp peak. So if you see that, you can just basically disregard it and say that's the proton from an OH group. Okay, quickly going over our molecules in question to see what their splitting pattern would be. So cyclohexane, top left. One chemical environment. Each of these carbons has 2 protons, so we'll get a 12 size peak there with all the protons. But the splitting pattern, the thing to notice, the splitting pattern is everything is exactly the same. It's the same chemical environment. Everything sees the same. So you actually get just a pure singlet here. Everything's exactly the same. So since everything is the exact same chemical environment, there's not a difference in the structural chemical environment, even though there's multiple protons adjacent. Since they're all the same environment, it doesn't matter. It's going to be a singlet. Same thing with the top right. It's the same thing. You've got 4 methyl groups, but each chemical environment is exact same. It's structurally exactly the same. So you're only going to get a singlet, a 12 size integrated singlet. Same thing with the benzene. You've got each proton has 2 adjacent protons and 2 different on both sides, and even more around it, but it's all exact same. It's all symmetric. It's all structurally the same, so it's a singlet. Now for the paraxylene, you have 2 different environments. Your methyl groups, they're exactly the same, and they see the exact same thing. There's no difference in them in terms of what they see or the structure. It's a symmetric molecule, so it's a singlet. Same thing with the benzene protons. They see the exact same thing, even though there's weirdness with one's adjacent, one's not, stuff attached. It doesn't matter. It's the exact same. Everything sees the same thing, so it's a singlet. So all 4 of these, even though all those weird things can happen with what we just talked about, all of these are just singlets because it's symmetric. Everything's structurally exactly the same. That's the key point. Now with our second group, we get a little bit more convoluted. Now we start getting into some multiplets here. So for our first molecule, even though we got that bromine group, which might affect some of the chemical shift going upfield or downfield, it doesn't do a thing to the splitting because these are all the same exact chemical environments. They're all structurally equivalent. So you're only going to get a singlet here. On the top right, we start changing things up. We've got 2 environments with the CH3 and the CH2, so different shifts, different environments, different integration sizes. But now adjacencies start to come in because this is not structurally symmetrical. This is not the same. So looking at A first, your methyl group, that has 2 adjacent protons. So that's an N+1 of 3, so that'll be a triplet. And then your CH2 group, the B, it has 3 adjacent protons, so that'll be a quartet. So you're going to have a size 3 triplet, and a size 2 quartet. Bottom left, you have 3 chemical environments, and it's not structurally the same. Even you have those 2 CH2s in the middle, but remember those are different. They're attached to different molecules. It's not symmetric, so those are considered different structural environments as well as different chemical environments. So your A group has, let's see here, your A group has 1, 2 directly adjacent, and that's going to be a triplet. Your B group is going to be complex because it's got 5 adjacent, but remember that caveat I said that it's got 2 groups of adjacent. A and C groups are both adjacent to that B group, but they're not the same group. They're not structurally the same. So then you get in a complex. So it's going to be a multiplet. There's probably going to be 7 to 9 little individual peaks for that one. So that's going to be a complex size 2 multiplet for your B. C has 2 adjacent, so that's going to be a triplet size 2. And then finally, your bottom right, you've got environment A, which is the methyl group, so it'll be size 6. And because of those, both of those only have that 1 adjacent thing, but that doesn't matter because they're both exactly chemically and structurally equivalent. So because of that, you don't even worry about the adjacent carbons. It's only going to be, sorry, there you do have to worry about it because the molecule isn't similar. It's you've got 2 different environments. So you have the 2 different environments of A. So it's going to be the adjacent carbon has that 1 proton on it. So it'll be an actual doublet. It'll be a size 6 doublet. Sorry if I confused you there. But the thing to look at with this molecule is we have different chemical environments. Therefore, it cannot be structurally equivalent. If you look at, for instance, the top left, where it was a singlet, you only have 1 chemical environment, and all of those they're all bound to the same thing. So that's structurally and chemically equivalent. So that's why it's a singlet. Whereas on this one, it's chemically equivalent. Both of those methyls are basically the same things in terminals of their environment, but it's not structurally equivalent because of the differences in the molecule, and you have a different environment. That extra proton on that CH is causing an overlapping magnetic field. So that's where the difference comes in. You have different chemical environments, which cause it to be not structurally the same. So you have 6 total size because of the 6 protons. It's got 1 adjacent. That central proton is adjacent to both of them, so that's 1. So that's why it's a doublet. And then B in the middle, this is one of those complex ones. It's not a true complex because you can actually associate this because there's 6 total adjacent protons, but they're in the same chemical environment, same structural environment. So you can say that's 6 plus 1 or septet for that one. And by now I'm sure you're getting kind of confused and things are starting to go crazy. Hopefully not too bad, but it's reading NMRs is tough, and that's why there's software made to read it for you generally. The stuff I imagine you would be asked on the quizzes from Dr. Mighty would be more simple type stuff. They wouldn't be too convoluted. I don't really consider these hard, but they take practice in looking at stuff here or there. So this is not something you can just pick up real quick. It takes practice. So. All right, moving on to our last set here. We've got the top left. We've got 4 chemical environments. So we're going to get a bunch of splitting from all the adjacencies. So for A, your methyl on the far right, you got 2 adjacent, so that's a triplet. For B, that's the methyl on the far left. You've got 1 adjacent, so it's going to be a doublet. For C, it's the CH2 without the bromine. You've got 4 total, but because they're not the same structurally, it's going to be a complex multiplet. And for D, it's also going to be complex because you have 5 adjacent, but they're not the same structurally, so it's another complex. So this will be a very messy spectrum. You'll have 4 distinct peaks, but they'll be split into triplet, doublet, and 2 complex. And then, of course, the chemical shifting will be different, and their integration will be different as well. Top right, this is a symmetrical molecule, but just like the last one on the last slide, the chemical environments are different, so you're not thinking that everything is just a singlet. So since the chemical environments are different, you have different chemical environments, you have to worry about splitting. So for A, your central carbon with the 2 hydrogens, there's a total of 4 carbons that are adjacent, and they are structurally equivalent. So you can say it's going to be 4 plus 1, or a quintet. It's going to be 5 peaks. And for B, you have 2 adjacent, so that'll be a triplet, and it'll be a 2-to-4 ratio based on the number of protons. All right, for your bottom left molecule, we have 3 different environments, and they're all fairly unique. So for A, for your methyl group, you have a total of, let's see here, no adjacent protons, because the carbon they're attached to on the benzene ring doesn't have a hydrogen. It's an sp2 hybridized, so that's it. There's no hydrogen adjacent. So it's just going to be a singlet. So it's 0 adjacent plus 1. It's always in plus 1, so it's a singlet. For B, you have same situation. You've got no directly adjacent carbons, so that'll also be a singlet. And for C, those are all benzene rings. They're all structurally and chemically equivalent. So even though there are some adjacencies, since they're structurally and chemically equivalent and symmetric to each other, that's just going to be a singlet as well. It's a little bit more convoluted because singlets, when we're talking about singlets with aromatic rings, there's always some little haze and some ticks on it because of the conjugated pi systems and the electron cloud that's associated with it, but it generally looks like a singlet. And then just throwing one extra in there, ethanol, just a 2-carbon alcohol there. We're going to do this one because we've got the proton on the oxygen too to show you. So got three chemical environments, 3 different associated proton environments. So your A, the methyl group, that has 2 adjacent, so it's going to be a triplet. Your B, the CH2 in the middle, has a total of 4 adjacent. But the key thing is here, the proton on the oxygen never really, like we said in the caveat, it doesn't associate itself with splitting because it's hydrogen bonding and moving around so much. So even though there's 4 adjacent, one of those protons is on the oxygen. You don't count it. You just account for the 3 on the adjacent methyl group. So it's actually just 3 adjacent. So that becomes a quartet. So that's they always ask a question like this in MR, and every single question I've seen is they throw an alcohol in there, and a lot of people miss it because you just get caught into the N+1 and adjacency and everything, and you forget that you don't count adjacent hydrogens if they're in an OH group. So you never count that hydrogen on an OH group. And then finally C, you have same thing. The protons in OHs do not account for adjacency or splitting. And since it doesn't account for anything else, it acts as if there are no adjacents. So it's just going to be a singlet. Your OHs will always, the proton for an OH will always be a singlet. It'll be broad on this, but it'll always be a singlet. It doesn't associate itself with splitting. All right, now after all that long discussion and going through each step, we'll look at the actual NMR readouts for each of these molecules in question. So the first one is cyclohexane. Like we said, this should be a 12 height value singlet based on the environments, and that's what we see with the NMR. And because of the shift, because these are secondary carbons, they're not primary or methanes itself, it's a little bit greater than 1 in terms of ppm. Our second molecule, which is 2,3-dimethyl-2-butene, same thing, same chemical environments. The molecule is symmetrical, so we would expect a 12 value singlet, which we see. But because we do have that alkene, and these are secondary carbons, we've got a large, the primary carbons, but they're attached to secondary, tertiary carbons, double bonds. So that's more shielding, so it's going to be further downfield, and we see that at about a 1.5 instead of the 0.9 for just a pure methyl proton. Here we have benzene, same chemical environment, same structural environment, 6 protons, so it's a size 6 singlet, and because it's an aromatic system, we expect it to be 7 to 7.5, and it's right around there, 7.3, somewhere in that range. And like I said, either you see that little extra peak down the bottom. Anytime you're working with aromatics, it always looks like you might have some multiplicity in terms of splitting, but that's just a common artifact of being a benzene ring because of the conjugated pi system of electrons. Now we come to paraxylene. This is where we are our first 2 chemical environments. So we've got 2 different peaks. We've got peak A, which is associated with the methyl protons. There's 6 of them, so it's going to be a size 6. And because it is attached to the aromatic ring, it's shielded quite a bit. We get a bunch of downfield shifting, and it's actually about a 2.2 or 2.3 for that peak instead of the 0.9 for a standard CH3 methyl proton. And then, of course, we've got the aromatic protons B, and that's generally anywhere from 7 to 7.5, and we see them a little bit more than 7 in this example. So it's a 6-to-4 ratio in terms of the area in those peaks, based on the 6 protons of the methyl versus the 4 protons of the benzene. All right, now we come to tert-butyl bromide, showing the effects of electron donating or electron density groups, polarity on the chemical shifting. Got same chemical environment for all the protons, so it'll be a singlet. There's 9 of them, so it'll be a size 9 singlet. But the deal here is it's a 1.7, 1.8 because of that bromine and the shielding increase and the downfield shift. So the shifting does quite a number, going from the 0.9 to almost close to 2 because of that single bromine. We come to ethyl bromine, bromoethane or ethyl bromide. We've got 2 different chemical environments, the methyl and the CH2 groups. The methyl group we expect a size 3 peak, and the CH2 Briard group we expect a size 2 because of the number of protons. Now in terms of splitting, A is going to be a triplet because there's 2 associated next to it, and B is going to be a quartet because there's 3 associated next to it. So as we see, A is a little bit further upfield because it's attached to a group that has electron density there with the bromine. So it's about a 1.6 or so. And then B is, because it's directly attached to that bromine, those are going to be a lot higher downfield shift. And we see it's at about a 3.5. So it's a big difference from the 0.9. Here we have the 1-bromopropane, the first with 3 different distinct chemical environments. A is your methyl group, and that's going to be a size 3 triplet due to the 2 adjacency. And it's going to be, even though there's a bromine in it, it's a few away, so it's going to be fairly close to that 0.9. As you see, it's right at 1, maybe a little bit above 1 as the center point of that triplet there. For B, that's going to be complex because you got all the different environments around there. And if you notice, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there's 12 or so distinct little peaks in there, maybe even more with you count the little nubs in the center. So there's a lot of little peaks there. But the key difference is it's complex. It's shifted because it's a little bit closer to the bromine, so it's shifted further up, closer to 2 than the 1. And then the size is going to be 2 because there's 2 protons associated in that environment. And then finally, your C environment is going to be a size 2 as well when you integrate the area into that curve. And this will be a triplet because there's 2 adjacent protons from the environment B. And it's even much further upfield because it's directly associated with the bromine, so it's 3.5 or so. So everything we've learned so far is kicking in with these. Here we have the symmetrical isopropyl chloride. Even though it's symmetrical, we do have different chemical environments, so it can't be the whole bunches of singlets. So we have 2 different environments, the methyl groups A and then the central carbon proton B. So the A, when you look at them, there's only 1 adjacent, that central carbon proton. So it's going to be a doublet. And it's going to be a size 6 because you got 6 protons associated in A. And it's going to be greater than 0.9. So in this one, it's showing it's a little bit higher than 1, probably about a 1.1, 1.2. Now B, it's got 6 adjacent, and they are structurally equivalent, so you can call it a septet. That's perfectly fine. It's not a convoluted thing. If you were to zoom into that glob, that big black glob, you would see 7 distinct peaks and no more. So you could actually count them zooming in. Or if you graph it, if you take the formula and graph it and expand it, you can see it very easily. But that's only going to be a size 1 because there's only 1 proton. But it's directly attached to chlorine, so it's highly shifted downfield. So it's about a 3.7, 3.6 or so versus a normal 0.9 for a pure methyl carbon. Here we've got the 2-bromobutane, which is a 4 chemical environment system with a bunch of splitting. So your chemical environment A, the far right methyl, it's got 2 adjacent protons, so it's a triplet, and it's a size 3 when you integrate it. And it's far enough away from that bromine where it won't affect too much in terms of chemical shift, so it's going to be around a 1, which is what we see. Now for B, it's another methyl, but it's closer to the bromine, and it's only got one adjacent, so it's going to be a doublet. It's going to be a size 3, but it's going to be further downfield because it's closer to the bromine, and that's what we also see. It's, about 1.7, 1.6, somewhere in that range. And then we come to C and D, which have different chemical environments and adjacencies that are not equivalent structurally, so those are all complex. So if you look at C, it's going to be a size 2. It's going to be super complex. And it's actually that those you see two little humps that are just a little bit past right around the 2.5 mark. That's when you zoom in, there's a whole bunch of little bumps and peaks in there, and that's what that complex is going to be, a size 2. There's tons of them in there. And then D is the proton attached to the carbon with the bromine on it, and that's the furthest upfield shifted. And there's a whole bunch. There's big peaks, small peaks associated with them, side peaks, tiny little nub peaks. So it's another complex that shifted the highest because of the bromine. Now you have the orthomethylbenzyl chloride. This one has the 3 distinct peaks with an aromatic ring in it. So A, your methyl peak, it's got no adjacent, so it's a singlet, and it's a size 3. But it is attached to the aromatic ring, so it's going to be quite a large shielding value, so it's going to be further upfield, and this is what we see with the singlet at a little bit past 2, about a 2.2 value there. Your B environment is your chlorine substituted methyl group with no adjacencies, so that'll also be a singlet, size 2. But it is also attached to not only the aromatic, but a chlorine, so it's going to be even more shifted than A, and we see that at about a 4.5 designation there. And then finally, we get another singlet associated with the benzene ring, which is generally between 7 and 7.5 in that range. But because it is the benzene ring and you got the aromaticity, the conjugated pi system of electrons, it's kind of fuzzy. It's a singlet, but it's kind of, it's got little jagged edges and all. It's not really defined spikes or peaks, but it's got the fuzziness. So you see that typically with aromatic systems. And then finally, just to show you one, we'll do ethanol. So this will be an alcohol. So we can talk about the proton on the alcohol group. So 3 chemical environments. A will be a triplet due to the 2 associated adjacent protons. It'll be size 3, and it's a couple groups away from electron dense groups, so it'll be greater than 1, but not a whole bunch more. B is going to be your OH proton. And remember, this has nothing to do with splitting. It doesn't associate itself with splitting, so it's always going to be a singlet there. And we see that singlet, and it's kind of hard to see because we're zoomed out, but if you zoomed in more, it's a fat peak. It's not a defined line. It's got a really big fat area underneath it, but it's only a singlet. So that's the key thing, singlet, and it's more broad than your standard ones. And then your C environment is going to be a quartet because we have 3 associated next to it. Remember, the proton from the OH group doesn't associate with splitting, so there's just only 3 that are associated next to it. So it's a quartet, it's size 2, and because it is attached to that oxygen that has the shielding, it's much further downfield. We stay at about a 3.5, 3.6 range. So this will basically bring an end to your NMR. I expect questions to be fairly similar to the 10 or 12 chemicals we've gone over, just basic, how many signals you're going to have, will this be shifted further downfield than this, what's the splitting like, what accounts for the splitting. You might even see some, diagrams of an unlabeled NMR, and they give you the molecule and they say which peak is associated with which group group of protons you're looking at. So basically matching, and probably some key concept, things of what causes splitting, what causes chemical shifting, stuff like that. So that's what I would expect. So hope you learned a little bit. Hope it was a whole lot of information. So if you're not too utterly bored with this stuff, but it's stuff we got to teach. It's very important in terms of chemistry and lab work especially. So hope you got something out of it and learned something, and I hope everything goes well for you.